Anyway. Yeah, question? That's fine. So factor analysis, we can take a look together. So I'm not covering it. It's a little more general than PCA, but not too much more. Any other questions before we move on? I was asking, what kind of resources or support can help you with linear algebra stuff. So this course assumes linear algebra background a little bit, but it might have been many years before when you took linear algebra, or your course wasn't covering what you needed, blah, blah. We all come from different backgrounds. It's all good, but I just don't have too much time. So we went through linear algebra in 3 lectures. Now you will take your time to review and ask me questions. And one feedback I got is exercises on Canvas. They're good to teach something new that maybe not covered in your previous linear algebra class. But if you're just trying to refresh already, it's maybe too much. So I'll try to find a little more leveled exercises. That's one feedback I got. I'll work on it. Anything else I could do for you guys for your linear algebra refresher or review or whatever else you call it? Yeah. Because linear algebra is basic, be good friends with linear algebra. It will help you a lot. Yeah, these firefighters are amazing. I think they already managed that big smoke going away. Wow. Yeah. All right. Now we will go to probability. So 3 fundamental things that runs in the backend of all algorithms that you will see is linear algebra, probability, and optimization. Okay, these are like 3 basics. And nowadays also you need to think about neural nets. And this 4 things is basically a good chunk of our course. Okay, that's our first foundational module. If you looked at your Canvas, that's the longest module. That's the foundation. So, okay, now I need to tell you what's probability. You don't have to read all this abstract notation, etc. It's actually something simple, but you need to be also precise. That's why I wrote it in a precise way. So let me tell you what is probability. You will have possible events happening, and you will attach probability a number between 0 and 1 to those events. Let's say you have a dice, and it's not like this Dungeons and Dragons stuff, just normal dice, okay? You roll it, and then what's the possible event? There's it could be 1, 2, 3, 4, 5, 6, right? There's 6 possible events. And if it's a fair dice, we say they all have probability 1/6. Okay? In general, you will have what people would call a universe. Universe is all possible things that can happen, all of them together. Okay, and then event in that universe is a particular event, like getting a 5 when I roll a dice, or getting a heads when I flip a coin. And then for all these events, you will attach a number on them. So this will be probability of that event. It should be a number between 0 and 1. Okay. If I look at all events together, the entire universe should have probability 1. What does this mean? This means I'm rolling a dice. What's the probability of me getting 1 or 2 or 2, 3 or 4 or 5 or 6? Since I thought about all possibilities, I'll get for sure one of them. So with probability 1, you'll get one of them. That's what this part means. And the last one is if you have disjoint events from each other, like getting a 2 or a 3, they don't happen together, right? If they're disjoint, probability of their union should be the same as take their probabilities 1 by 1, sum them up. Okay. And if you satisfy these, you have a probability setting for yourselves. And this covers all, possible probabilities you could do. For example, probably you heard of normal variable or Gaussian. It's not something like rolling a dice, it's more continuous. That thing also satisfies these assumptions. Okay. So this is the basic assumptions you have to satisfy, right? And then, okay, let me not get into that part. All right, now, for example, let me just do a quick example, like I try to do at the beginning of lectures. Suppose you have some stuff that satisfies these assumptions. And how would I write probability of A union B in terms of probability of A and B and maybe their intersection? Any ideas? All right. Why? So that was a very good guess. Yeah, but in the assumptions, I only have disjoint stuff. So yeah, okay, I'll not make you. This is say A minus B, this is say B minus A, and this is say A intersection B, right? So then probability of A union B will be A minus B plus intersection and B minus A. And then you will write this stuff in terms of these and that, and then as you said, you're counting this twice, it will cancel, you'll get here as you intuitively saw. All I'm trying to say is, as soon as you set these assumptions, this type of stuff follow immediately. That's what I'm trying to say, okay? So, the thing works out as you expect it to work out, right? But some stuff in probability is counterintuitive, though. At least in the first sight, your intuition gets used to it, and we will do some of those examples as well. Okay, and now the next thing is conditional probability. So which means if I know A happened, conditioned on that, what's the probability of B happening? This is equivalent to taking intersection probability, dividing it by A, okay? Because if you know A already happened, let's think about it again with our potatoes. This is A and B, right? And you know A already happened, so this A already became your universe. You're already there. And then what's the probability of B happening? Well, only the intersection now, right? So that means you take that part and then you divide it by your entire universe. That's the idea. That's conditional probability. This, you can also write it as follows on the other way around. Intersection is the same thing as B conditioned on A times A. Or you would do it the other way around. Intersection is the same thing as A conditioned on B times B, okay? This might look silly for the moment. We will apply it very soon, okay? This stuff is basic but important. So far, so good. So we would call two events independent if the intersection probability is the same thing as take probability of one, multiply with the probability of the other. For example, let's say I have a dice and a coin. What's the probability of getting a 5 and a heads at the same time? Well, you first compute the probability of getting a 5, 1 out of a 6. Heads, half, you multiply them. Literally, this is what you're doing. Because the coin and dice are independent from each other. You're intuitively doing it, okay? So now here's a, okay, before I get to the example, let me also define conditional independence, then we will do this example, or I'll ask you to think about it. So sometimes events are not independent, but when you condition them on something that is known to happen, they start looking independent. What do we mean by that? A intersection B conditioned on C will be the same thing as A conditioned on C, B conditioned on C, multiplied. This means they may be not satisfying this. Maybe they were not independent. As soon as we assume C happened, they look independent. It's called conditional independence. And in this lecture we got on causal inference, you can think about it something like this as an intuitive picture. Here is your A, here is your B, here is your C. And when you assume C, A and B does not have an edge in between because they look independent. Intuitively, you can think about it this way, okay? All right, and this conditional independence, sorry, it should have gotten next to this one. Yes. Conditional independence underlies a lot of stuff. Okay, that's a very basic and important idea. Okay, now here's an example. You got two events, their intersection is empty, but they are not empty themselves. So their probability is not zero. Are they independent or not? Please think about it a minute or two using the definition right up there. So you took this randomized algorithms class last semester. So you're not allowed to talk now. So you have seen this type of stuff in that course? Yes. Yes, why? Yeah, that's right. Yeah. So you say probability of intersection is 0. That is true because intersection is empty. So this guy is 0 because it is the probability of empty set. Okay. Now we need to ask, let's follow the definition. When do we have independence? This has got to be equal to this times that, right? So let's check if this is equal to this times that. So am I going to have probability of A times probability of B 0? Well, they're both non-empty, so likely this is not going to happen. Okay. So this is like what I was trying to say. A lot of stuff in probability is counterintuitive at first sight, and you get used to it as you do. So like, yeah, exactly. That's what I said first time when I saw this too. Two events are not intersecting, so they got to be independent. But no, they're actually dependent in the sense that they're mutually exclusive. When one of them happens, the other doesn't happen. That's a dependence. Okay. All right. So far, so good. Any questions? Everybody happy? Okay. And now what else we got? Look, I have one more exercise, looks like. Let's skip over. I could put this on Canvas. I was trying to ask similar stuff with like conditional probability. Or should I skip over or not? Yeah, let's not skip over. Can you look at this example also? I got two events now, like the one before their intersection is empty. And turns out we know when an event C happens, this A doesn't happen. A conditioned on C, probability 0. Now, is A and B conditionally independent given event C? Suppose C already happened. Of conditional independence? Yes, exactly. That was the question I was trying to poke. This is the definition of conditional independence. A intersection B conditioned on C should be the same thing as A conditioned on C times B conditioned on C. So A conditioned on C is given to be 0, and A intersection B is 0. Is empty set. So this is going to be 0 too. So you'll get a 0 on the left and right. Actually, this time the answer is yes. So they'll be conditionally independent. Okay, this is yeah. Go ahead. Like I can also zoom out so that is it good now? There you go. And this is all recorded as usual. Okay. So far so good. We are slowly warming up to probability. Okay. Is everyone done taking notes? Looks like, yeah. Okay, now the next word you would hear a lot in probability is something called a random variable. So what's a random variable? It almost looks like what we already talked about. It takes some events and attaches some probability to them. But the point is, for a random variable, some events may not have any probability at all. Maybe it's like 0. Okay. So let's say the universe for you is all possible temperatures that can happen in a city. Okay. And then our random variable happens to be the temperature in San Antonio throughout the year. And suppose it goes between 20 and I don't know, 120 in the summer, so somewhere between. So if you ask me the probability of this guy being, say, 10 Fahrenheit, then it's going to be 0. Okay. So that's the only difference. So it takes some events from your universe, attaches a probability to them. Right? That's what a random variable is. And sometimes you would see a word called sample space of X. This is not a pun intended for SpaceX. It means like all possible events allowed by your random variables. So for our San Antonio temperature example, sample space is say between 20 to 120 or whatever else it is. Okay. All right. Now then, depending on your sample space, your random variable is sometimes called discrete or continuous. So a continuous example is say a uniform number between 0 and 1. You got the whole interval as your sample possibility. A discrete is something like dice coin. You have a discrete possible outcome. And if you dig deeper into this, we will get into a whole bunch of philosophical discussions and complicated math. So I will not answer any such questions. If the world is continuous, is it discrete? How do I know something is measurable, probable, blah, blah, blah. So all this stuff, I'm not saying they're not important questions. They're just not related to this class. So, for example, if you're really interested, you could take a one semester course on something called measure theory, which is trying to think about what kind of places we can construct some probability. Okay. Or once I had a student who was really into philosophy, he couldn't let it go. Always kept asking me a whole bunch of philosophical questions about what is random, what is deterministic. We have quantum mechanics. Are we living in a discrete world or a continuous world, blah, blah, blah. So we will not get into any of that, right? We will use probability to do some algorithms. That's our purpose. Yes, go ahead. Whatever. Yeah, but I will put one fun video on our canvas, which has a lot of insights in the connection between computing and probability, and kind of has the perspective that randomness is in the eyes of the observer. I'll not get into, as I said, all this stuff. Some of it is rather important, especially for cryptography purposes, if your random numbers are actually random or not. I'm not denying the importance, just that not relevant to this class's purposes. Okay. All right. So now, if you get a dice and if somebody asks you what's the probability of getting a 1, when I roll it, you will say 1/6. Now, let's say somebody says, I have a uniform number between 0 and 1. What's the probability of getting a half? Wow. So people say 0 right away. Like, I'm trying to say, like, does this question even make sense? Kind of like, it's a uniform number. If I pick any particular number and ask what's the probability of getting that, and if you say 0, then it's probability of getting anything is 0. So what the heck is going on? So you get into some like issues right away. So the way to get around this is you start asking more continuous questions to continuous random variables. Okay. So what is the probability of getting 1 was a very discrete question. So what's a continuous question you could ask? What's the probability of being less than a number? For example, I take a uniform number between 0 and 1. What's the probability of being less than 1/3? Then you can immediately say it's 1/3, of course. And then I roll a dice. The thing I'm trying to illustrate here is the same question still makes sense even for discrete stuff. If you ask what's the probability of getting output less than 3.5, you will say 1, 2, 3, 3 out of 6, half. Okay. So this question makes sense for continuous and discrete alike. This is called usually CDF, cumulative distribution function. Sometimes people also call it probability distribution function, but then it starts getting confused with probability density. They will have the same PDF. Okay. I would like to call it cumulative, so we know they're not the same thing. Yeah. Okay. Now we define this cumulative stuff, and suppose we made sense of it. Now, next question is, what do I do with continuous random variables? How do I compute anything with them? A good idea is if this function f we defined, if it is something I could look at how it changes when I move the number from, say, a to a plus a small delta, then I could maybe understand how this probability is behaving. And that's the derivative, right? If you're looking at small changes, that's going to be a derivative. So let me remind you, this is a fancy way of defining derivative. Okay. So what is it? You push it tiny bit. You say minus what it was. You divide it by the push delta. And you send that delta to 0. This will give you the derivative. Okay. I'm showing you this because it's going to become relevant to our discussion. Not that I want you to prove this or anything. Okay, that's not my purpose. So now let's plug this into our definition. For us, this had a meaning. Ft means what's the probability of being less than t. Right? And let's plug that in. So give me a sec to get rid of this annoying little thing here. All right. So if I plug it in, what I get is right here. This means probability of being less than this. This means probability of being less than that. So if you take probability of being less than t plus something and minus being less than t, what else you have as an option? That means you got to be between this number and that number. So you're literally looking at probability of your random variable x being bigger than that guy, because you're subtracting all the probability of being less than that. And you're started off from being less than this already. So you're looking at probability of lying in that small interval from t to t plus l. This you can compute for continuous or discrete. That makes sense for all of them. That means that makes sense to take derivative of this thing, okay? And that's called a probability density function. They will usually denote it with a small p. So as soon as you know the probability of being less than a thing, everything else follows through. That's all I'm trying to say, okay? To get the density, take the derivative of cumulative function. Cumulative is all about like, what's the probability of cumulatively being less than a number? And then take derivative of that, it will give you the instantaneous change, which will be the density. So these are the two main things that makes probability go. Now let me give you some examples. So you will see this guy all the time. We did not define mean and variance. You'll get there soon. This is your good old Gaussian. And you'll usually see it denoted by some mean here and a variance here, or mu and sigma squared. And if you plot the density, it will look like this. Around that mean, it will like peak, and it will go very quickly, decay pretty fast, okay? And the density of this guy, so this t and this should be a t. Would look like this, for example. The reason for very fast decay is if this t is the same thing as this mu, you will get a 0, so you will get 1 over something here. And forget this stuff here, that just makes things normalized. Forget about that, don't worry about it. Just look at here, and you will see why it's decaying very fast, okay? That's an example you will keep seeing all over the place. This is Gaussian random variable, and it's its density. Okay, let me see. And yes, exactly, so probability density function. Let me go for it again. Right here, PDF. And that's literally the derivative of cumulative distribution function. Okay. So now if you have any calculator or anything around you, suppose you get a Gaussian with mean 0 and variance 1, and try to plug in half to it and tell me what you get. So here the mean will be 0 for this guy. This variance will be 1. Can somebody with a calculator do plug and check and tell us what happens to the density at half? So the 0 and 1 guy will be peaking at 0. I'm just trying to get a sense of the fast decay to see at half, where is it? Right? Okay, anybody with a calculator? Can you just plug this into the density where this is 0 and this is 1 and tell me what you get? So dice. Yes, exactly. It's a very good question. So how do I connect continuous and discrete in terms of this density function question? You can think about exactly like probability of getting 1 for a dice is 1 out of a 6. So you could think about it like a density, just putting some weight there, like 1 out of a 6. That is true. Cumulative means being less than a number. So give me a number and then ask me, what's the probability of being less than that? So you're accumulating till that number. That's why it's called cumulative. So let me picture you the cumulative. So this is the density. And suppose you give me a number t. So cumulative will look at everything less than this. So hopefully you remember your fundamental theorem of calculus. What does it say? Integral and derivative are the inverse of each other. What's the meaning of an integral? The area under a curve, right? So this was my density. It was given by derivative of my cumulative, right? So let's say my cumulative was big F. And when I take derivative of this, I got my little f, right? So that means if I do this area thing to my little f, I should be getting my big F. Because area is integral. If you take integral of a derivative, you get back what you started off with. So this whole area here will be your cumulative probability function. Okay, I hope this now sticks a little better as a mental picture. So far, any questions? Anybody who bothered to compute this? So times what? Okay. So the only point I'm trying to make here is like at 0, here you'll get nothing. Okay, so let me put it out. And Farhan says when you actually push it to do something, 0 point. Okay, so only at half, you already dropped a lot. So this type of stuff, if you go like 1, 2, you will see dropping even faster. This type of stuff we would call light tails. So tails are very thin. There's like a big peak in the middle. It's just going very quickly, very small numbers, okay? Now I'll show you some other examples where the tails are a bit more heavy. And the reason for that is like, let's say you have some data and you want to fit some distribution to it, okay? And if you're fitting Gaussian, a small data point way out there could change your entire thing because the tails are so thin, it's extremely sensitive to errors. But if you want something that is more robust, then you'll do something that is close to Gaussian, but not exactly. And there are many ideas for this. One of them is called student T distribution. I'll show you today. And the reason it's called a weird name, student T, is like the guy who found it was working for a brewery in Ireland. He wanted to create a distribution which fits his experiments. And he only had small data, how much you could try with beer. And then the company thought this is an extremely valuable insight. So they didn't let him publish with his name. So he published the thing with just author student. So it's ended up being called student T distribution. And we still use it to this day. For example, you would hear a tool called TSNE, T stochastic neighborhood embedding. And that's the student T distribution, okay? And we use it because tails are less sensitive than Gaussian. All right, so now I got one random variable. I talked about its cumulative probability function and the density function. Now, how about if I got two of them? Suppose you have two random variables, Z and U. RV at this point means random variable for us until it's summer and you had on your RVs, right? And then, sorry, yeah, I couldn't stop the dad joke since I deal with my kids all day. So, and then the joint cumulative distribution will mean this, literally give me two numbers, cumulatively look at first one being less than that, second one being less than that. That's about it. You know, for only one variable, we only defined it like this, right? For two, give me two numbers. Cumulatively, I'm asking both of them being less than that, right? And when you plug in infinity to this, second one will not have any constraint at all. Being less than infinity means nothing. That means when you plug in infinity to that, you will get back the cumulative function of the first one. Okay. And if you would plug in infinity to the first one, you will get the cumulative function of the second thing. So if you have the joint function, you can always recover back single functions by plugging in infinity. And now, let's see what I was trying to say. So far, so good. And then to get the densities of individuals, what do? I take derivative of that cumulative functions. How about when I have two of them? What does it mean to take derivative of a function with two variables? Well, take the partial derivatives, right? So you take partial derivative with respect to first variable and the second variable. That gives you the joint density, okay? So to take joint density, you have to take derivative with respect to both components. And that means take partial derivatives with respect to both of them. Yes? I don't think so. It's fine. Okay, so far so good. And now, how about independence? Independence can be seen in three equivalent ways. Just calling them independent. First way, not so useful. Second way, you look at their densities. The joint density, which you get this way, partial derivative, should be the same as taking individual densities and multiplying them. And the third way, which is equivalent, joint cumulative function should be just given by multiplying individual cumulative ones. Okay? And now let's do an exercise on this definition. It's looking a little abstract. So, yes. I have a joint cumulative function for two random variables, z and u, and it's right here. Could you please check if they're independent or not? I'll give you a couple of minutes for this. Let me zoom out so you see everything that I have written. And you would need to use here from joint, you first need to go to individual ones by plugging in infinity. Then you need to check if this definition is satisfied or not. Okay. And from the definition, they don't look independent at all, at least to me. This needs to be factored out into two things. Okay. Yeah, I'll wait because, I could talk and talk, but I think it's hard to remember if I keep talking and talking. Think about it a couple of minutes. I think this will help you retain. Is the writing legible? So this is a minus, and A and B doesn't matter what they are. If you don't like them, just make them all one. It's okay. Right? The answer would be the same, whatever A and B you got there. How is the probabilistic PCA stuff going? We'll get there soon. I feel. Okay. Very good. Yeah. Very good. I think they're independent. Why? Okay, we gotta work through this slowly. Or maybe let's wait a minute or two more. People are still thinking, I guess. Then I'll wait what you got. Yeah, I think so. And I tried to make up when I was writing the notes. So it's not from any particular source. So. I think at least you're warmed up. If you solved it or didn't solve it, I hope it's okay for time purposes. I talk about how to go about it. So I plug in infinity to one part. So this is joint. If I plug in infinity for one of them, literally this gives no constraint on that. That means I'll recover the cumulative of the first guy. And let's see what it is. When you plug in infinity to S, this will be 0. Suppose, as I said, let's say A and B are just 1 or any positive number would be fine. Let's forget about them for a second. When you plug in infinity to this, e to the minus s, e to the minus infinity will be 0, right? Okay. And this will be 0 too. So only survivors are going to be this and that term. So when you plug in infinity for s, you end up getting 1 plus e to the minus t. Now let's plug in infinity for the first component. This will give me the density of the second one. And this time I'm plugging infinity for the variable t. Well, this is going to be 0. This is going to be 0. I will only have, yeah, question? So far, so good? I thought somebody's asking a question. Okay, very good. Now let's multiply these two things and see what I get out of it. Because if they're independent, the multiplication should be equal to the joint cumulative function. That's what I need to check. That's how independence is checked, right? That was the definition. Let's multiply them. And when you multiply them and expand the thing, you will see, you will get what I gave you at the beginning. So that means they're actually independent, okay? And a priori, it's not clear at all that they were independent, okay? The punchline from this is like independence is something you better check using computation unless it's very obvious. Okay. If I'm rolling a dice and a coin, okay, they're independent, fine. But other than that, try to compute this stuff and see if they're independent or not. So far, so good? Yeah, you will get the same answer. Yeah, you'll take derivatives of this stuff, compute the densities, then you will see the factorization as well. B is equal to, yeah. You'll have to take derivatives of this stuff, compute the individual densities, then take twice partial derivatives of that guy, compute the joint density, and check if the joint density is equal to multiplication of individual densities. Yeah. And you will see, yes, that's the case. Right? Very good. So say it again. Yes, exactly. So we end up checking, yeah, this checked out. The question mark is yes, they are independent. Very good. Now, how about conditional density type stuff? Let me see what I want to do. 25 minutes. Let me see what I want to do in the remaining 25 minutes. I want to show you at least one algorithm every lecture. Okay. I think I can do this in 25 minutes. Okay, so conditional distribution and density. So far we talked about independence. Then I also talked about conditional independence early on. I told you how to check independence using densities and distributions. Now we need to also talk about conditional independence or that kind of stuff using densities and distributions. Okay, very good. So now if you think about like, I know y is less than or equal to b, what would be the probability of x being less than a? Then you will take like joint, divide by this, it will make all sense. Fine. Even if they're continuous or discrete, this sounds good. But suppose y is continuous and somebody asks you this. I know y is continuous, say y is a uniform between 0 and 1. And we did the experiment, y came out as half. We know it now, fine. What's the probability of another continuous being less than something? Now it's getting tricky because this was uniform, it was a continuous thing. How do I reason about this being like precisely equal to a number? And when you do the experiment, it's gonna be precisely equal to a number at the end of the day, right? Okay, very good. Well, one thing you could do is you can again try to do this trick, right? So think about y being between b and a little perturbation and take a limit and whatnot. And this actually works out, okay? So being equal to b could be taught this way. You know, even if it is continuous, when you give it an interval, it will make sense. And if you can do this limit, I don't know if we can do it or not for the moment, then this would make sense again. Fine. And that works out. I'll not do all that math. Some math happens there. And then what happens is this: probability of x being less than or equal to a and y being equal to b turns out to be the integral. Start from the smallest value this x can take, go until the upper bound that is given to you. And what are you going to integrate? You take the density of y at that particular point b, because you know that happened, okay? That's going to be your denominator. And on top, b is fixed now, because y is b. And x will run through all the values between -infinity to a. And you will put the joint density right there. And you will integrate that ratio, okay? That's what's going to come out after you do all that math. And because of this, this will essentially give you like a conditional density situation. Okay, and we'll get to that soon. This is like the essence of the idea. Take the density of the thing you know that happened, put it in the denominator. It's like your universe now. And on top, take all the values x could take that is allowed from a to -infinity, integrate it over. You will get your answer to this. And now this is like a cumulative question. And when you take derivative of a cumulative thing, you will get your density. And that's going to come out killing this integral and something like that soon. Okay, very good. Now, exactly. So this will be defined as the conditional density, the ratio you have seen there. And it's usually denoted as such: x conditioned on y, TS, meaning you would assume y had the S value. And what is the probability of x being T now? That's what you should think intuitively, okay? And this is called conditional density. And you could also write conditional density of y conditioned on x in the same fashion. And if you look at these equations from a different angle, the joint density here is equal to conditional density times this guy, right? This guy right here is this times that. You can also look at it from that angle. Joint density of two random variables can be seen as take the individual density of one of them and condition the other one on top. Okay? And you can pick any one you like. You can also pick y and condition x on top. And you will arrive to your joint density. This also kind of makes sense, right? So I'm trying to look at jointly x and y. What are they doing? Look at y first. And when you know what y is doing, look at what x does conditioned on that information. And this logic flows through all the cumulative densities and everything when you do the math, okay? So some people even went into the extent of claiming probability is the extension of usual Boolean logic for science, because it follows all these basic logical ideas you would have. You know, we have all these zeros and ones that we build everything over, right? And this most famous one was called Jaynes. And there are things attached to his name called Jaynes maximum entropy principle, Jaynes such and such principle. If you're interested, take a look. So some people have that perspective, like see the probability as a language of sciences, basic sciences, because it follows the Boolean logic rules, more or less, that you had built your stuff on top. All right, very good. Conditional density, conditional independence is when. So now independence and conditional independence. So this was the definition of independence. The density should factor out. Okay. Sometimes you would see this logic people writing it like this: x is orthogonal to y. They're independent. They have no relation. That's how they would look at it. And now conditional independence. Let's say I got x and y. They're not necessarily independent. But when I condition them on a z, they start looking independent. This is conditional independence. This will look like this: x and y conditioned on z on, say, 3 values right here. Is going to be the same thing as condition x on z, the condition y on z, multiply them. And the intuitive picture for this is this graph right here. Okay? So in this causal inference lecture, was this guy called the mediator? I forgot the names that he was given. So confluence, okay. So basically, this Z explains the behavior of X and Y. When you have the Z, they start looking independent from each other. That's the idea. And sometimes you would see people writing it like this. X and Y are not related. They're independent, orthogonal, when you condition them on Z. And the extension of this idea is something called graphical models. If you would do machine learning very seriously, you would talk about graphical models. We'll not do much of it in this course because already the fundamentals we have to cover will take the semester. Okay, but graphical models is the basis of a lot of stuff. And it goes like this, basically. You're trying to understand relationships between certain randomness. Okay, very good. And now bias rule. What's the bias rule? Well, here's the bias. Here's bias rule in short. So let's go to the definition. A conditioned on B was A intersection B divided by B, right? And we know A intersection B can also be written as B conditioned on A times A. This is equal to that. If you remember, we talked about this when I did the definition. And then this is staying there. When you look at it, if I write this thing in short, this is how bias rule will look like. A conditioned on B is the same thing as B conditioned on A times A divided by B. And this looks rather dull if you look at it this way, like, well, okay, so what, right? I just did some algebra. But the punchline here is like, if you think an event B happened, and after that, trying to understand, after that knowledge, what's the probability of A happening? This would be equivalent to thinking, when A happened, what was the probability of B happening? So you're reversing the order of things. Algebraically, it looks very like, okay, so what? But when you think about this practically, it has implications, okay? And now let's do a little more of this. And I think I will be able to give you a naive Bayesian classifier today. So this is the first way to write it. And then for discrete stuff, you could also write it like this. What is the probability of X being T if they're discrete random variables? What's the probability of my, I don't know, summation of two coins being two heads, or summation of two dices being 15? They cannot be 15. I made up so that. Summation of two dices being 10 when I know the first dice is blah, something like that. So this is the discrete version of the same story. You can reverse the order of dependencies, and then continuous version of the same story will go through the densities. Density of X conditioned on Y, same thing as Y conditioned on X times X density divided by Y density. This is bias rule, basic bias rule, okay? Now let's do some examples to use this. Here's an example. In the textbook, there is this example of this Monty Hall problem. That's very nice. I just don't want to spend time on this. I would recommend reading it. We are probably all, I don't know if anybody watched that game show that this guy comes in. There are doors. Okay, you seem to know. And then he opens one of the doors. So behind one of the door, there's a fancy car, a Ferrari, say. And the others, there is a goat. Okay. And then there's like, say, the number of doors is not really important. Say 3 or 4. Okay, 3. Okay, let's say 3 to make it simple. And this guy, and you pick one of the doors. And if it is the right choice, you will get the car. If it is the wrong choice, you will just get like a mess out and you'll go home. Okay, and you pick one, and there is 2 remaining. And the guy opens one of them, and there comes a goat. And now remaining 2 choices. One of them is a car, one of them is a goat. And the game show host, Monty, says, do you want to switch now, or you want to stay with your choice? Okay. And there is a mathematically advantageous strategy in this game. And you could figure that out using bias rule. I'm not going to do that just because of timing. Otherwise, I think it's a lot of fun. But it is done in the textbook also, so you can just read. Now we will do something else just to illustrate the bias rule. Suppose you got 3 coins. This could happen actually on this like if you're buying something from street, right? So there's this people sell you stuff, they do all the tricks. Right. So like 3 coins, one of them is biased. The other 2 are fair. Fair ones are like half-half, heads, tails. Biased one is biased towards heads, 2/3, tails 1/3. But we don't know which one is biased. They all look the same, as far as you can tell. Now you do an experiment. You flip them. And it comes out as head, tails. That's the experiment. Now the question is, now what's your estimate on the first one being the biased one? So you know one of them is biased. They all look the same to you. Before the experiment, if they ask you what's the probability of the first one being biased, you would say 1/3. I have no idea. They all look the same. 1/3 first, 1/3 second, 1/3 last. Now you did some experiment. What would be the probability of first one being biased after your experiment? So this is what Bayes rule is all about. After you have some data, how do you update your probabilistic estimates? Okay. This boring algebraic looking thing has this meaning. That's why it is useful. Okay. Now this is my event. Heads, tails. And let's say first E1 is the event of first one being biased. E2 is the event of second one being biased. E3 is the event of third one being biased. Okay. Now B happened. I am asked to estimate probability of E1 conditioned on B. That's my question now. So before the experiment, they all got the same probability. First one could be biased, second, third, I have no idea. Okay. Now after the experiment, what I'm asked to compute is E1 based on B. Let's apply Bayes rule. Bayes rule says this is B based on E1 times E1 divided by probability of B. Correct? Now this I know. Before my experiment, it was 1/3. So I'm going to plug in 1/3 here. And this I should be able to compute. What was B? I forgot I should look. Heads, tails, I think. Right? And if I'm assuming E1, that means I'm assuming the first one is the biased one. So first one being heads will be then 2/3. This will be half, this will be half. So in this rule, all I'm trying to say is I could also compute this one now. If I assume E1 was what happened, I could compute. Now how about computing probability of B? That's the part you need to maybe think a little bit. And here is how it goes. Probability of B can be written as probability of B intersection E1, intersection E2, intersection E3. Why? Because E1, E2, and E3 are completely disjoint from each other. E1 means first one is biased. E2 means second one is biased. E3 means third one is biased. Let me draw you a picture to illustrate this. Let's say this is my universe. This is E1. This is E2. This is E3. And then your B event is something here, right? And now B is divided into 3 pieces. That's all I'm saying. B probability first piece plus second piece plus third piece. Now, why is this any useful? Well, intersection is the same thing as conditioned on that times that, if you remember from definition again. You can do the same for here, same for here. Now I can compute everything. I will say, okay, probability of E1, 1/3. When I assume first one was biased, I could compute this. Probability of E2, 1/3. When I assume second one is biased, I can again go compute heads and tails. Same for here. I'll compute all these, plug that in right up. This I know, this I know. You will do all that computation, you will get your answer. Okay. Let's see if I want to do it or not right now. No, I think I don't want to do it. You guys, I recommend you do this computation. It's going to look like this. It's not hard, but as you do it, you get used to it, all right? Because you'll see actually some number which you may not be able to guess a priori just by like intuition. Okay, so this is how Bayes rule is applied. And as I said, another fun thing is this game show problem. What's a good strategy? This is done in the textbook. I recommend you read it too. It's a lot of fun also. Likely you will not forget that game show example through Bayes rule. So it will help you retain the information, okay? Now, why do we care about Bayes rule? Well, here's one example. Very good. It's called naive Bayesian classifier. Here's our problem. We got some data. It could be image or something else. Let's say image to fix our imagination. I would like to do image classification. Let's say this is good old handwriting data, okay? Means data. And then what are the options? The labels could be 0, 1, 2, up to 9. And then your image could have 28 to 28, 784 many pixels. So it could be a vector with like this many features. Okay, so you got your vector with this many features, and you're going to put a label next to it. This data is 1, this data is 2, whatever. Very good. Now, if I look at it from a probabilistic angle, this means when I know my pixels, conditioned on that, what's the probability of label being 1, label being 2, label being 9? That's what I need to estimate, okay? And then what you're going to do, look at all these probabilities if you would know them, and then look for the label that gives you the maximum probability and print that out as your guess. But of course, this approach would be rather memory intensive. You have to save all these probabilities and you have to also compute them. Both memory and computation time, this thing doesn't look good at all, okay? And now, if I look at the same thing from a bias law perspective, y conditioned on x is the same thing as x conditioned on y times y divided by x, okay? Now, don't forget, this x has got many features, like 784. Y is just a label, okay? So if this x has got like d features, this thing right here actually looks like this. Like d features, all of them, conditioned on y. This means like this. Your label is actually 5. The digit is actually 5. Now, what conditioned on that, what is the probability of the first pixel being this, second pixel being that? You know, that's what this is asking. If I try to use Bayes' law to do this computation, okay? And now you could also do this thing like one by one in the following sense. You're talking about all d features conditioned on y. You could start with the first one. And when you got the first one, second one conditioned on that and blah, blah, blah. You could go that way too. But this is still very cumbersome. Still doesn't help much. Now here, what does naive mean in this algorithm? We will assume a lie is true, which is features are conditionally independent from each other. That's the simplifying assumption, okay? Suppose when you condition them on the label, features become independent for a second, okay? Then how does this help? Well, then, like if I'm looking at, say, the last feature conditioned on everything, including y, since they will be conditionally independent, this is going to be just this. If I assume this thing is true, which is not going to be true, but if it is close to the truth enough, you might get a decent algorithm, okay? Then I could just get away with computing this. And now computing that is not that bad. That means for this label, you're just going to do some sampling from your data. And literally, you're going to do counting now, okay? Look at the ones that have a label 5 next to it. Look at that 100 feature and see the probabilities. With, 5 of them is such, 10 of them is such. Then you will assign the probabilities accordingly. This is just now clever data structure question. You just need to do clever data structures to count these probabilities. It's literally a counting problem now. And then what I will do, well, I'll plug that in here, this guy, this whole multiplication into the Bayes law. Also probability of a label. Again, this is just counting. You sample your data and there are like 10 labels and you see which one happens with which frequency. You say, okay, with one out of a 6 probability, I keep getting the 5, whatever, okay? So all this could be estimated somewhat efficiently, and this gives you a model to guess the labels, okay? And this is called naive Bayesian classifier. And it actually works much better than you would expect. This thing is based on a lie. Those features are not conditionally independent. But when you have so many features, they start looking kind of independent. Okay. And if you got nothing else, you could run this algorithm. It's implemented in all libraries. Okay. This is like the first thing you could try. It's nothing fancy. You will do better stuff than this. But already using Bayes law gives you a classification algorithm. That's what I'm trying to say. And if you want to play with this, just go to say scikit-learn naive Bayesian classifier. See how people play with it and enjoy yourself. And I'll try to see if I have a notebook on this or not. I still got 2-3 more minutes. Okay, very good. This was our Bayes law and naive Bayesian classifier. Let's see what I want to do after this. Okay. So what did we do so far? We started definitions of cumulative probability function, probability density function. We talked about independence, conditional independence. We talked about Bayes law. And we have seen an algorithm now that is based off of Bayes law. And the entire branch of statistics is born out of this idea. It's called Bayesian statistics. Okay. And there's like two main schools of thought in statistics, Bayesian or frequentist. And they keep fighting each other, okay? And I'll not get into that fight, obviously. But this is so important that it gave birth of a whole main idea, school of thought in statistics. That's maybe what I'm trying to say. Okay, what we will do starting next lecture is I'll go through some classic random variables. Then as soon as we go through them, probably we will learn logistic regression. And after that, we will learn about what is an expectation, what's a variance, such and such. And we'll move forward from there. Okay, that's about it for today. Thank you so much.